Good morning, everybody in AP Chemland. We are going to start with Chapter 4 on chemical reactions and solution chemistry. And this first part will be review, so it'll be a little quick like Chapters 1 through 3 were. You guys did an outstanding job on that last exam, so I was very proud of you guys. And I think this first part will be review, and then we'll slow way down when we start talking about redox, and we'll all be on the same page again. So hopefully a lot of these terms will come back again, and we're just trying to get those cobwebs out. So the first thing we're going to talk about, that water is a universal solvent. And why is water such a good universal solvent is because you've heard the term that it's highly polar. Well, again, we just need to remind you of what highly polar does mean. And remember that when we look at water, water is a bent molecule, and if you remember the term electronegativity, it means that it has a positively charged end and a negatively charged end. So if you look at this structure over here, recall that water has these lone pair of electrons, and these lone pair of electrons take up a lot of space, and they are going to repel each other ever so slightly, and so it's going to cause the angle between the two hydrogens to be a little bit smaller, and causing that electronegativity difference to be between them a little bit greater. And so we also did electronegativity lines where we had the positive sign on the hydrogen and the oxygen is more electronegative, and so the pull was to the center, making an uneven charge, and that gives it its bent shape. So again, it's highly polar because of the positive and negative ends, the bent shape due to those lone pair of electrons that we just drew in there. And then we need to remember that when things are dissolving, that there's a lot of space between the water molecules. And that space is going to allow things to be dissolved. And so hydration, we just have a term here, the addition of water to an ionic solid. And whenever you see the ionic solid, we are thinking of salt. You should be thinking of a metal to a non-metal, where the electrons are transferring, which is going to result in dissolving. And so the space between the water molecules is going to allow an ionic solid to take up that space until there isn't any left. And for us, we would visually see then some salt falling to the bottom of the beaker or the glass or whatever you have. We are going to be doing a lab later in the week that's going to address aqueous solutions. And so we're going to remember how to write molecular, complete ionic, and net ionic equations. So that dissolving process that I've been mentioning, because water is highly polar, I want you to take a few minutes and really look at this diagram. We can see that we have this salt crystal. I can tell that this is my salt. I can tell that it's ionic because it has a negative, a positive, and a negative, and it is in an orderly pattern. And if I were to take a razor blade and I were to cut along any end here, it would fall along the pattern or the shape of the crystal, whether it's cubic or rhombic or whatever it is. And then you can see the water molecules coming in, and they are going to orientate themselves on the side so it can dissolve. So you can see over here, if you focus in on this part right here, we have the water molecule coming in to dissolve that salt. And the positive side of the salt crystal, the cation, is being attached or attacked by the negative side here of the oxygen. And so there's an attraction there. And then they just continue to pound away or dissolve or remove parts of the crystal until if there is no more dissolving that takes place or there isn't any more space. And you can see that by these larger diagrams here, how many water molecules are attached to the cation and the anion. And there's a strong attraction there. If you guys look at this net ionic equation right here, you can see that we have our salt crystal dissolving into the sodium ion, the cation here, and then we have the anion of the chloride ion. Again, remember the positive charge means that it has lost an electron, and the negative charge means that it has gained an electron. Ions move independently of each other, even though we see that it's NaCl and it's a salt crystal. When they are ions, they're moving independently, bounce around in the water, attracted to the ends of the water molecule. Okay, then Factors influence that dissolving. Surface area. You can understand surface area if you think about a sugar cube versus granular sugar. There's definitely going to be the difference in the rate of dissolving there. The temperature. If we raise the temperature of that sugar solution, we're going to be able to dissolve some more sugar into it. Agitation means we are stirring our solution. Oh, I can't spell stir, I guess. We are going to be stirring our solution and causing that agitation, so the more of the salt crystal or whatever crystals you're trying to dissolve can be into that system. Energy of the system, endothermic versus exothermic, depends on the type of bonds, and then the bond strength. Both of these, chapter number 4 and 5, are going to be something that we're going to talk about later as we move forward. Okay, and then the very last thing that we talk about here is how can water dissolve a non-ionic substance? All right, so we have heard the term that like dissolves like. We may have talked in last year talking about polar dissolves polar and nonpolar dissolves nonpolar. We didn't really cross too much in the different types of molecules that could have both ends. So if we look at our water molecule right here, we can see that this is ethanol. So our formula here is C2H5OH. And that OH there is called an alcohol functional group. And that alcohol functional group can be seen right here. And you can see that it has an end very similar to water and does have an affiliation for it because it has the difference in charge. We know that oxygen is slightly negative, hydrogen is slightly positive, and because there is that difference in charge, water is going to be attracted to it. Now, if we look at the other end of the molecule, the CH3 here and the CH2, there is no difference in charge. It's perfectly balanced, so there isn't an affiliation there for water. But water is going to dissolve something that is non-ionic because it has the alcohol or the OH for the functional group. Soap is another example of this. Even though we say that polar is going to dissolve polar substances, nonpolar is going to dissolve nonpolar substances, and we also say that ionic substances will dissolve in polar substances like water. But it doesn't have to be as strict as this. We can take a look at a soap molecule. A soap molecule has a polar end and it has a nonpolar end, so that we can take the soap and dissolve the oils on our skin or in our hair, and then it can be washed away in the polar water that we have. So there's lots and lots of molecules out there that actually have more than one functional group on the end, so that water can work in a variety of systems. Okay, that is section first part of chapter 4. There'll be one more podcast on section 4.2. I hope you have an awesome day, and I'll see you in class.